Okay, let's begin. Picking up from where we left off. So we're still in chapter 10. And we learned about what a finite set is. We learned about what the numeral sets are. We learned about countable sets. We learned about uncountable sets. What else do we talk about? Numerical equivalence. Talk about non-numerical equivalence. What else did we mention? We spoke about what it means to have smaller cardinality. And we ended up with the continuum hypothesis. I think that's where we ended. Continuum hypothesis. Basically, there is no S such that the size of S is between these two cardinalities. Okay. Where this guy is a stand-in for the size of the natural numbers, and this guy is a stand-in for the size of the real numbers. Let's quickly review what's a finite set. How do we know a set is finite?
Cardinality of equals to n.
Is some n. Right? Some finite number. You can actually count them. You might be counting for a while, but you can actually count them and finish counting them, and it will be some natural number. Denumerable means
Cardinality of a is equals to the cardinality of the natural
right.
number.
Cardinality of A is equal to the cardinality of n. And how would you show that that is true? Create a function from A to n that is bijective. And again, the functions might be very complicated to actually write a formula down for, but as long as you can use some descriptive process that is unambiguous and you know will not miss any of the elements, that is actually fine. So countable sets is basically your finite or denumerable. The uncountable means infinite, but not countable, in the sense that you cannot create a bijection from that set to the natural numbers. Where it is sort of talked about in general what this is here, it just means there's a bijection. There exists f from A to B, where f is a bijection. So normally if you want to prove that, you have to prove that there exists such a function. This means there does not exist f from A to B, such that f is a bijection. This guy means there is an f from A to B, such that it is one-to-one, but there is no onto function from A to B. Right? And then in such a case, we say that B has a larger cardinality. We kind of showed this. We're going to see another way to see this, but we kind of saw we've suggested that the cardinality of n is strictly less than the cardinality of r, using the Cantor's diagonalization argument. Right? We pretended that there was some bijection, but we realized we would miss someone. That kind of suggests that there would be no onto function from one to the other, but we didn't get too specific into exploring that. But this is actually the case. So these guys are two infinities. The size of this guy I call Aleph naught, the size of that guy we call C for the continuum. And the continuum hypothesis is the assertion, or the hypothesis, that there is no guy in between There is no infinity in between these two infinities. So this is the baby infinity, and that's their older sibling, and there were no children in between them. Okay? And we also mentioned that the mathematician Godel, which is, his name is, he's German, so they have that. I don't know what that's, I don't remember what that's letters called. But Godel proved that you can't prove the continuum hypothesis. And then the other guy afterwards, I believe it was Cohen, are inspired by the work of Godel, proved that you can't disprove it. So this is kind of a statement that based on our axioms, we can't really prove and we can't really disprove. It's kind of a hypothesis that people tend to just believe. Right? So this is the smallest infinity there is. This is the next step up. There is no in between. And that kind of highlights one of the things in mathematics where there's probably people who don't really go far in math, is probably always looking on wondering, what's wrong with these math people? Why are they looking at it? How can you come up with something like that where your math can't even handle it? It's a mathematical statement, and you're telling me that there's no way to prove it using the math? Like, how can you do that? Develop this whole system of things, of which, within that system of things, you can't prove something. What is the point of that? Proof is the whole idea, isn't it? And you have things like Fermat's theorem, a very simple theorem. People take hundreds of years to prove that. And then you have a theorem like this, people working on it for years, and then ultimately someone proves it. Oh, we can't prove it. Oh, we can't disprove it either. We have no idea if this is true or false. We kind of sort of believe it. And it's like, are math people masochists? What's wrong with them? Why would they torture themselves with things like this? Why would they work on things that they are not even sure if there's an answer to it? And it turns out Godel went a lot farther than that. Godel is, you can think of him as sort of the Heisenberg of mathematics. So you know the Heisenberg uncertainty principle from physics, right? You can't simultaneously know the position and velocity of an electron, right? The more you're confident about its position, the less confident you become about its velocity, right? So you'll never be uncertain. There's an uncertainty principle. It turns out math has its own uncertainty principle, and Godel was the guy that figured it out. He has two major theorems that he's known for, the incompleteness theorems. The first one basically says that in any axiomatic system capable of solving elementary arithmetic, that system will necessarily have statements that cannot be proven within that system. Statements like this have to exist. So it's not that mathematicians are masochists and we like playing around with this. No, this is a reality that is forced on us. By setting up an axiomatic system, we will necessarily, you will have to generate statements in that system that cannot be proved by that system. And it cannot be remedied. So you might say, why not just take this as an axiom and put it in the system and now we can prove it? Well, it turns out you just create some other statements that you cannot prove. It is literally impossible to prove everything in mathematics. Mathematicians will encounter statements that cannot be proven or disproven. So not only is this statement such a statement, but Godel proved that in general there are such statements, like there has to be such statements. His second incompleteness theorem was even more disheartening. Basically he said, even if we pretend we could create a system that we could prove everything within that system will necessarily generate inconsistencies, meaning there will be contradictions within that system, two contradictory statements side by side. So if I pretend we could create a mathematics in which we can prove or disprove everything, within that mathematical system we'd be able to prove 2 + 2 is 4 and simultaneously it is 5, right? So this kind of thing is the lesser of two evils. There will be things in math that are unprovable, and you might not know ahead of time what these things are. Someone has to prove that it's unprovable. But yeah, systems like this will exist. This is probably the simplest one. There are many other statements that we know are not provable. Others that we're still not sure whether they're provable or not. But usually they're all very complicated to even understand what you're talking about. This you can kind of explain, okay, there are two infinities, we know one is bigger than the other, we're not sure if there's one in between. In terms of just how big these infinities are, I want you to start appreciating, because this is it's a lot of things, right? There are a lot of things in here. But I want you to know just how, when I say there are more real numbers than there are natural numbers, I want you to understand just how much we're talking about. In fact, if you were to take the real numbers and throw away all the natural numbers and find how many things do I have now, right? So I took this many things, I threw away an infinite number of things. How many things are left? Turns out, it made no difference whatsoever. So when I say this infinity is larger than that infinity, I mean larger by a lot, right? I can go to R, and I can throw away all the rational numbers. It's still R, right? If I can throw away any number of countable sets from R, I can take away any union of countable sets from R. I can take away a countably infinite union of accountable sets. I can subtract that from the real numbers, that many things, and it will make no difference. It's like I have an ocean, and you took one drop out of the ocean and threw it away. It's still an ocean. So when we say this is larger than that, I don't mean, oh, it's just a few things. No, it's a lot larger. It's like, this guy's nothing compared to that, right? And what we're going to find out here is that we can make guys even larger than this guy, such that this guy is like nothing. Like I can throw away all of those guys and literally have no difference whatsoever. In fact, such a thing is, which we'll prove today, is the power set of subsets of R. Right? This is strictly larger to the point where I can take this, throw away that many things, and it's not going to make a difference. And you can keep going. I can keep taking power sets and build on things. Each so large that if you threw away all the previous ones, it's the same. There's the same number of things here, right? So dealing with infinities is very weird. So this is why, if you realize that we're being very careful when we're talking about something, no, be careful how you're counting. It has to be a bijective function. We're like anal about it. It's like we have to be, because infinities can get very weird and very counterintuitive when you're dealing with them. So we're actually going to prove a statement like this today. The fact that a set is always strictly less than its power set. And we're even going to show how to write R as a power set of the previous things. So let's actually jump into that. Then we end with the Schroeder-Bernstein theorem, which is very helpful because, again, finding functions like this, like a bijective function, they can be very difficult in general. So the Schroeder-Bernstein theorem helps us to be able to prove this without technically actually proving it. And so that's where we are. So let's actually jump right into proving a statement like this. And that's where we're going to start. Theorem. Let A be a set, then the size of A is less than the size of the power set of A. So we're not going to prove all the theorems that we mentioned today, but this one we will prove because it illustrates a nice technique that you might want to use later on. Proof. So let's deal with the throwaway case. Either A is the empty set or A is not empty. In the case of the empty set, we know the answer, right? If A is the empty set, then the size of A is 0, while the size of the power set of A will be 1. So the claim is true for the empty set. So assume A is not the empty set. We're going to show that it will still always be larger, the size of the power set. And again, it's painfully obvious for finite sets that this is the case, because n is always less than 2 to the n, which we know is the size of the power set. But since infinity is very weird, we need to know that our intuition from the finite case actually carries over, because it doesn't always carry over, right? Like if these two sets are finite, that's not true. It's not true to make the statement. But in the infinite case, we can make such statements. So we have to verify that, yes, in the finite case, it makes sense, but we have to verify it can never make sense, even in the infinite case. So we don't want to really. So here I'm just assuming A is a non-empty set. It may be finite, it might be infinite, it might be countably infinite or uncountably infinite. It's not going to matter. We want to prove this in general. So what we're going to actually do is prove that there is a one-to-one function that goes from this guy to that guy, but there's no onto function. So that means a bijection could never be created. But because we can connect guys here with guys over there in an injective way, it means that there is at least this number of things contained in there, but there are more contained in the set. So clearly, we can take an injective function f from a to the power set, given by f of some element just going to the set containing itself is 1-to-1. Okay. So I can just create a function from f to its power set where each element maps to the set containing itself. So that's a 1-to-1 function. So I know that A is less than or equal to B, or A is less than or equal to the size of its power set. Now to prove that it is strictly less than, I need to show that there is no onto function. We're going to do this by contradiction. Assume to the contrary. There is some function g from A to its power set such that g is onto. We're going to show that this gives you contradiction. It's not going there. You cannot find no onto function. So here's where the proof techniques comes in, and we've sort of used it before. We're going to create a set to contain a certain number of things that we care about. And we're going to show that we're going to use that set to get our contradiction. So we kind of did this with when proving that well-ordered principle implies the mathematical induction. Okay. So let's collect B to be the set of all elements in A, right, which is our domain set, such that A is not in G of A. Now, that might be a little bit confusing, so let me sort of explain by an example. Did I have a specific example so I don't have to think about it? Okay, yes. So, here's the example. Let A be the set 1, 2, 3. Okay? And suppose, so let F go from A to the power set by, if I take f of the element 1, the output here, I want it to be 3. And if I take f of the element 2, let that be, it mapped to the set 1, 2, 3. F of the element 3, I want that to be equal to the set 1 and 2. Right? So we know all the elements contained by the power set of A. It contains 8 elements, these are 3 of them. Right? So 1, map it to this set, 2, map it to that set, 3, map it to this subset, right? So then, what would the set B be for this example? Okay. I want to find the set of all elements such that they're not in the image, they're not in their own image, right? For example, if I plug in 1 into my function, it maps to 3. Notice that 1 is not an element of this. So 1 would be my set B. 2 maps to this set, but 2 is an element. So it's not in B, right? Because it's contained, it's in its own image under this function. 3 maps to this set, 3 is not in that set, therefore 3 is also in B. So for this particular example, my set B would look like this. So I'm claiming that such a set would always exist. So I'm just looking for the set of elements that when they go to a subset, they're not actually a member of that subset. Okay, so that would be an example. So that's the set B that I'm creating. I'm going to show that this set, which clearly should exist, right? At the very minimum, it's going to be the empty set. If it's the empty set, it's going to disprove it. But we're going to show that such a set cannot exist. So here's where we're going to do. Since G is onto, for all B subset of A, there exists some B in A such that G of B equals B, right? That's what onto means. I'm just applying the onto definition.
Do you mean powers?
Come here.
For all B subset of
Yeah, this means B would be an element of the power set. Right? B is clearly going to be in the power set. Right? Because it's a subset of A. The power set is the set of all subsets. So I'm saying for all elements in the domain, for all elements in the codomain, there must be an element in the domain such that the function maps to that element. That's what onto means. Right? So B subset of A means it's an element of the power set. So here's the thing. We have that either B is an element of B or B is not an element of B. That is a tautology, so I can say that, right? So it's kind of like this. Either the guy is a member of the image or he's not a member of the image. One of the two things have to happen. Even without this example, that is a statement that I can always make. Okay? So let's do each case. Assume B is in B. Then, what does it mean to be in B? Right? It is an element that is not a member of its own image. Then B cannot be in G of B. Right? Because if it's in the set B, that's the condition that makes it in the set B. But G of B is B by our assumption. So G is in B and so end up with B in B and B is not in B at the same time, and that's a contradiction. If we assume B is not in B, right? Meaning it's not a member of the set, means this condition is not fulfilled. Then that means B is a member of its image under this set. But again, G of B is B by assumption. So we get that B is in B, B is not in B would imply that B is in B. And that's another contradiction. G cannot be onto because it would give us a contradiction. Because we're assuming contradictions cannot exist because of Godel. Which, by the way, ironically, that's another thing that we were not sure. There's this idea that math has to be consistent, that contradictions cannot exist. Technically, we don't actually know this. We can't actually prove that math is consistent. I think that was one of Hilbert's problems. Prove that math is consistent. Yeah, can't really do it. You have no idea if it's consistent or not. But we're assuming it is, so contradictions cannot exist. But yeah, that shows that set is always smaller in cardinality than its power set. There's definitely a one-to-one function from this to that, namely just send every element to the set containing itself, but there is no onto function from this to that, because if we assume there is, that would lead to a contradiction. There will be some element that is both in a set and not in a set at the same time, and that clearly can't happen. So, for example, the size of n is strictly smaller than the size of the power set of n. Which, by the way, that means it's smaller than that set. Right? So this is the set of all functions from n to a set of size 2. And the size of n is smaller than that. Okay. So here's a question. Just how much bigger than n is 2 to the n? What do you think? Is 2 to the n countable? I mean, if you have an n, right? You can cross product it with n, and that's still countable, right? You can cross product it with q, still countable. Cross product with z, still countable. You can actually do this a countably infinite number of times. Still countable. You can multiply this by a number, still countable. We can do all sorts of math on this set, and it's still going to end up being countable. But what about exponentiation? Does that maintain being countable? Turns out the answer is no. 2 to the n is uncountable.
We could just use the thing that you just proved, right? It's less than
I know it's less than. So, yeah, if from the last class I mentioned that all countable sets are equivalent, so that also tells you right away it's not countable.
Yeah, I mean like from here, the thing that you just proved now.
Yeah.
I mean, you can just.
From last time, we know that if A, B are countable, then it must be the case that the size of one is the same as the size of the other. In fact, there's another theorem here. The size of this set is actually equal to the size of the real numbers. So that is that would give you another proof that the real numbers are actually larger. This proof is actually long. We won't prove this, but it's in the text. But they actually showed it. You won't need to construct such a complicated proof for this class, but it's in the text if you're curious how they managed to show that. So it's uncountable, but it's the smallest one of the uncountables by hypothesis. So the size of a set is always smaller than the size of its power set. The size of the power set of the natural numbers is actually the size of the real numbers. So when you take the power set of a set, you get another set that in the infinite case is so huge that that set can literally go from the countable variety to the uncountable. Its power set will go to the uncountable variety. And if you take the power set of that, it's like a super uncountable variety. Yeah, so these guys are huge. The size of the real numbers is huge compared to the size of the naturals. Let's see here. Yeah, so here's where we're going to talk about the Schroeder-Bernstein theorem. Right? So, in fact, you know that the size of n is smaller than the size of r. That would be smaller, by the way, than the size of 2 raised to the r. That is super smaller than the size of 2 raised to the 2 raised to the r. Right, but you can keep doing this. You're just creating power sets, right? That's something we know how to do. So we're looking at the set of all subsets. These are all, they will increase in scale. You can actually create a countably infinite number of sets, each larger than the other by a lot. So at any given time here, if I can throw away all these many elements, it won't make a difference. Like I can take this set here, throw away as many elements as is contained in all the previous ones, and it won't make a difference. Right? That's just how big you can get by taking a power set. It's a very large set. Now we're going to look at the Schroeder-Bernstein theorem. It's sometimes called the Cantor-Schroeder-Bernstein theorem. But your textbook calls it the Schroeder-Bernstein theorem. We're not going to prove it. It's another thing that's very complicated to prove. But I'll just make the statement. We'll take away some conclusions from it. So the theorem says, which I'll call SVT. SVT says, let A, B, B sets. Then, if the size of A is less than or equal to the size of B, and the size of B is less than or equal to the size of A, then it must be the case that they're actually the same size. Specifically, what you want to take away from this is that if there exists f from A to B, such that f is 1 to 1, and there exists g from B to A, such that g is 1 to 1, then there is some bijection from A to B. So basically, you prove the existence of two one-to-one functions in opposite order will imply that there's a bijection that exists. So again, curious, you can read that theorem yourself. We're not going to prove it. It's a lot to prove. In terms of intuition when reading it, you might think of Hilbert's Hotel. There's a nice little mathematical paradox that people like to talk about. Having that paradox in mind while reading the proof might be useful too. So do you guys know about Hilbert's Hotel? Okay, so basically it's a hotel with an infinite number of rooms. And every room has a guest in it. It's a countably infinite number of rooms. And then a new guest shows up. And it's like, okay, can I get a room? And they're like, sure, you can get a room. So what they do is they take the guest from room 1, put him in room 2, take the guest from room 2, put him in room 3, and do this forever. So the first room opens up, and then they put the guy in that room. So yeah, and then he has a bunch of people coming over, a bunch of his buddies from the football game. There are a countably infinite number of them show up to this hotel with infinite rooms that have everyone in the room. And they're like, okay, here's what we're going to do. Take the first guy in the first room, move him to the second room. Take the guy in the second room, move him to the fourth room. Take the guy in the fourth room, move him to the eighth room. In other words, you shift by an even number, right? Take all the guys in the odd number of rooms, move them to the even number of rooms. So you create an empty set, an empty room in all the odd pockets, and then you can put all those guys in there, right? So it's kind of like if you have a hotel with a countably infinite number of rooms, you will always be able to fill it even if you have a countably infinite number of guests coming in, right? By doing this reordering thing, you shift things around. And that's kind of the idea that Schroeder would use to actually make this argument. He's saying, basically, you can think of the rooms as the codomain and the guests coming in as the domain. And he's like, if there's an injection in either way, they're the same number of things. You would always be able to fit one guest to one room in all these cases. That's for the countable case in intuition, but that's basically Hilbert's hotel. People mention it all the time. And so this hotel that's it's never filled to capacity. If you have like the real numbers show up, then they're in trouble. But short of that, they'll find room for you at Hilbert's hotel. There's a room for everyone. Okay, so this is the Schroeder-Bernstein theorem. Let's see an application. So, the claim is the following. The size of the open interval is actually exactly the same as the size of the closed interval. Kind of would make sense if you think about it, where these are intervals in R. Okay, kind of makes sense. You're throwing in two more people. It shouldn't change the size of the infinity. But again, with infinity, we have to be very careful. We can't just assume, okay, I'm just throwing in two more guys. That's not going to bump it into a new cardinal number. It shouldn't. And this is sort of the principle by which you can show the other statement I was mentioning. The fact that you can throw away two guys and still have the same number of things, that same principle tells you you can throw away a countably infinite number of guys and still have the same number of things. So let's actually, to show this, to show it directly is kind of complicated. Why? Because it turns out that any bijective function that will connect these two will necessarily not be continuous. So you'll have to create some sort of weird piecewise function in order to get this done, right? So we actually showed that the open interval between 0, well, we showed that any open interval, a, b, doesn't matter what length it is, we can map that to R via some function like that. But since that function has to extend from infinity to infinity, from negative infinity to positive infinity, it's kind of hard to get the endpoints in there. You kind of have to like create a gap somewhere and show that you're not changing the size, and that's kind of difficult to do. So finding a bijective function from this to that is sort of difficult. But with something like the Schroeder-Bernstein theorem, we don't need to be able to do that. So to prove this, you don't end up having to find a bijective function, which would be not continuous and kind of hard to come by. All you have to show is that there's a one-to-one function from each one to the other one. So proof. F going from this guy to this guy by f of x equals x is 1-to-1, right? Just send every number here to himself in there. It'll definitely contain him, because this guy has all the elements that are greater than or equal to 0, less than or equal to 1. This guy has those strict inequalities. So every member in this set is automatically a member of that set. So that is 1-to-1. And let's find a function from this to that is 1-to-1. Right? The identity function can no longer work because, of course, sending 0 to itself is not going to work. 0 is not here. Sending 1 to itself is not working. That's not here. Right? And I don't really want to worry about a bijection, by the way, because that's going to be confusing. So what I can do is maybe send this guy to a smaller subset of that guy in a 1-to-1 way, and that can be done in many ways, but here's one of them. G of x equals something like x over 3 plus a third. then if you look at the image of this entire set, right? What is the smallest it could be? Well, it's when x equals 0, right? So that would give you a third. What is the largest it can be? Well, that's when x equals 1, and that would give you 2/3. And that is actually inside of this guy. But G is 1 to 1. This means that the open interval is less than or equal to the closed interval, and the size of the closed interval is less than or equal to the size of the open interval, which means these two guys have the same number of things by the Schroeder-Bernstein. Right, so it's a very useful theorem because it allows you a way to escape having to find a bijection, because bijections can be very complicated. A lot of times, just finding functions that are only 1 to 1 is going to be a lot easier. You do half the work and you get all the rewards. Well, you have to do half the work twice, right? You have to show there's a 1-to-1 function this way and a 1-to-1 function that way. Once you can show both, then it turns out that the only time that can happen is there is the same number of elements in each set. So it's a very powerful theorem, super useful. It allows us to prove two things that have the same number of elements without strictly proving that using bijective functions. We can just use two 1-to-1 functions and accomplish that. So that's the Schroeder-Bernstein. So if you're ever in a bind trying to prove the size of two things are the same, try proving that there's just injective functions in either way, which tend to be easier to come up with. And you can prove they're the same that way by hitting them with the Schroeder-Bernstein. Let's wrap up chapter 10. Consider these two theorems. They just go through this theorem A and B is what your textbook calls them, so I'll call them the same thing. And it says, let A, B, B sets, then one of the following must be true. Either the size of A is less than or equal to the size of B, or the size of B is less than or equal to the size of A. Or they're the same. I think they put strict. Now, if you look at that statement, it seems painfully obvious, but that's because you're using your intuition from arithmetic, right? Clearly, for two finite number of things, this is clearly the case. But as we've been mentioning, infinity can throw a lot of things into the work. What if they're countably infinite? What if they're uncountable? It turns out that this thing that was clear for any other finite numbers, sure, either 1 is less than 2 or 2 is less than 1 or they're the same. That seems to be clear, but that's only clear in the finite case. So it's not actually super clear to prove this one. To prove this, you actually need the axiom of choice. Which I'll mention a little bit about that in a bit. Right? That had its own controversy. It's less controversial today, but at some point it was very controversial. Yeah, mathematical controversies. Theorem B is basically the Schroeder-Bernstein theorem. So if A is less than B and B is less than A, then A equals B. So that's the Schroeder-Bernstein theorem. And by the way, theorem A would imply a theorem B. So if you assume these are the only three possibilities for the cardinalities of sets, then Schroeder-Bernstein is inescapable. This, of course, though, requires that you accept the axiom of choice. Right? So without the axiom of choice, this might not be true and that might not be true. But we are assuming the axiom of choice in this class. And today, most material that you read in mathematics would accept the axiom of choice. If they don't, they'll announce it. We do not accept the axiom of choice. Okay. So there are many ways to state the axiom of choice. So let me state that. I mentioned it a couple times, and I mentioned it's controversial. You might wonder, what the hell is he talking about? What is the axiom of choice? There are many ways to actually state it. I'll give you two very common ways to state it. So it says, for every collection of pairwise disjoint sets, there exists at least one set that contains exactly one element from each the sets are non-empty. From each of the non-empty sets in the collection. Equivalently, this is another way to state it. A choice function exists i.e., there is a function that takes a set of sets as its domain, where the image of each set is a member of the set. Might still be a little confusing, so let me give you an example. Let's say I have a set of things, like 1, 2, here's a set A, B, C, here's another set X and Y, here's another set Bill and Ted, right? So I have a set of sets where they do not intersect, they do not overlap, they're pairwise disjoint. No two sets have the same number of things. Then we can create a set. Let's call it A. So I'm going to create a set, and it's going to contain exactly one member of each of these subsets. In other words, I can take a function from this set to the union of all of them, such that it goes here, picks one of these guys. So let's say I pick 2, put in my set. I will go here, pick one of those guys, so I put B into the set. Go here, pick one of those guys, let's pick X. Go here, choose one of those guys, let's pick 10. So I can create a set in this way, right? Which you just saw me do it, so yeah, obviously you can do that. In the infinite case, it's not that obvious, as well as the fact that you can describe it by a function is also controversial. Why? Because you can't always actually describe this. A function should be a rule that is well understood, it's well defined, we know how it works, so we know what we're getting. Even in the finite case, it can break down. So for example, I think Bertrand Russell came up with this example, the same guy who argued that there can't be a set of all sets. So let's say you collect all the pairs of shoes in the world, right? There's all the pairs of shoes in the entire world, billions of pairs of shoes, okay. You can create a function to choose one of each of these pairs, right? You can actually give me a definite rule. Choose all the left shoes in the pairs of shoes, right? Clear. That's a function, fully understood, well-defined. If I look at a pair of shoes, I know which one to pick. I can choose, I can make this choice out of all these pairs of shoes. Where you need the axiom of choice is with the socks. Because now it's not clear anymore, is it? Socks are indistinguishable, right? What is the rule to pick one sock from the other? How can you well define choosing the socks? Right? What do you mean? Just pick a sock at random. That's not a function, bro. That's not well defined. Just pick one, just like you did here. Just pick one. Yeah, but that doesn't tell me a function exists. Right? So that's why it's an axiom. Because you can't really say what that function is. It's very easy to come up with an example where you feel like you should be able to do it, but you can't say how. And that is a problem. Right? Because that means you can't define a function. But this axiom just says a function like that always exists. There's a function you can create that will pick something in a definite way. Right? So that's the axiom of choice, which is very weird to some people that you can say that, because technically, we need some sort of definiteness to describe a function. You need a rule. Whereas the rule is not always clear. Couple that with the fact that the axiom of choice is equivalent to a lot of things that are troubling. Made its acceptance very dubious to a lot of people. There's, by the way, there's a Wikipedia article on this. All the things, like a collection of things that are equivalent to the axiom of choice. And one of them is equivalent to the well-ordering theorem. Now remember the well-ordering principle that we had for the natural numbers? Right? Every subset of the natural numbers has a least element. Right? The well-ordering theorem takes the well-ordering principle, puts it on steroids, and says, you know what? Applies to every set. Right? Meaning, we can always find a method of ordering for any set such that it will be well ordered. Right? So remember we said that, for example, the open interval from 0 to 1. To us it didn't seem well ordered. It is not well ordered. But that's well ordered by this guy, by the ordering mechanism that we're used to seeing from arithmetic. Sure, according to that rule of ordering, arranging things, this is not well ordered. The theorem claims, don't use that method. Use some other way of arranging things. There is a way to arrange things such that even this set will have a least element. And every subset of it will have a least element. There will be some guy that is smaller than or equal to every other guy with respect to that method of arranging things in order. Right? So you have the axiom of choice equivalent to that, which is crazy it turns out that it's also equivalent to other things that seem clear, or should seem clear if you get certain things. Like any countable set is smaller than any uncountable set. Right? Seems clear. It turns out if you want to prove that rigorously, you kind of need to invoke the axiom of choice, because you're not applying to anything that's familiar. It's not like I'm comparing natural numbers to real numbers and I can find functions and I can do stuff. We're saying, no, this will work in any instance, right? Which kind of makes sense when you think about it, but to write down a rigorous mathematical proof, it requires you assuming that we can make choices in this kind of arbitrary way. So it's equivalent to things that seem to make no sense. It's also equivalent to things that seem, yeah, of course, why not? So, yeah, that's the little spiel on the axiom of choice. Most people today accept the axiom of choice because we can do a lot of things with it. That's basically why. They chose it because it's super useful. Math is a lot more interesting when you have the axiom of choice available than when you don't. And so, you know, while we're not sure that math is consistent, while we're not sure, while we know we can't prove everything, it's more interesting assuming this.
Professor, I have a question.
Yes.
Are there people that do math on other systems besides the decimal system? Because I feel like all of this stuff is like related to that, right?
Well, yeah, but they're not going to be like, I mean, saying they're people, they're not going to be your typical average Joe.
Yeah.
There are mathematicians who are very, but yeah, like no one would know what they're talking about. Right. But yes, there are other systems that are not like anything we've seen before that a few people are working on.
It's like being insane in your own way. Like
Yeah. Yeah, being insane, but no one locks you up because you're smart. Yeah. Oh, he has a PhD. He's obviously okay. He can function. He's not dangerous. He's just in the room locked up by himself talking about it. Just leave him alone. Yeah. Yeah, but Godel sort of like, yeah, no matter what, there's going to be gaps in your knowledge. You can never know everything. It's basically what that's saying. You cannot set up a mathematical system in which you can know or not, or know everything is true, or know what is not true. It's just not going to be. It's not in the cards for a mathematician. There will always be things like continuum hypothesis. But that's the lesser of two evils, because if there aren't things like continuum hypothesis, then you have contradictions existing. So you choose one or the other. We don't like contradictions, so let's go with the fact that let's set up systems where there will always be gaps in our knowledge. So mathematicians are not the guardians of absolute truth as we once thought. There are gaps to a knowledge that any mathematician can achieve. Which on one hand is disheartening, on the other hand, that kind of makes it exciting, right? I mean, that's real. Like, imagine you're playing checkers. Checkers is a solved game, right? Meaning you can program a computer that it will always win if it goes first, like for sure. Like it's a solved game, and you can predict moves in it to the point where you can always win. So if you're playing against a computer that has this program, what's the excitement? You know what the end game is gonna. I'm gonna lose. Okay, move to you. Right? There's no, this is mystery. Godel is like the mystery. Oh, this might work out, but I might waste my entire life. You never know. You're rolling the dice. And that makes it exciting. Maybe math people are masochists. I don't know.
I feel like STEM majors or like humanities majors would make things super rigorous and like try to justify every casual thing.
Yeah, but basically Godel is like you can't justify everything. There are things that are unjustifiable. We're going to move on to book 2. And we're going to cover some of the highlights because a lot of this actually goes over things that we have done before. So in chapter 1 of the second book, This is elementary analysis by Ross. Which, as I mentioned, if you can go to the Springer website for that textbook, and as long as you're on the college Wi-Fi, you can download it for free. Try to download it at home. I don't think it would work. But on college campuses, you can actually download the PDF for free. So you can get that. So that's the second book. We're only going to be looking at some parts of chapter 1. Maybe the first 4 sections. I think the 5th section is the extended real line. This is where we pretend infinity and negative infinity are real numbers that we can manipulate algebraically and all the consequences of that. We're doing the highlights because some of it regurgitates things that we know about already. So chapter 1 will go over what induction is, but we already covered induction. So we're only going to really be picking and choosing the things that are of some consequence. So this is the standard textbook for advanced calculus that we do here. There's a small chance that for those of you who might be taking advanced calculus in the fall that your professor would choose some other book, but typically this is the guy they go for. If they would choose another book, you can probably also look into Principles of Analysis by Rudin. It's called Baby Rudin. Because Rudin wrote 2 books on analysis, and one of them is super difficult. And Baby Rudin's Principles of Analysis might be one that a professor would choose. Real Analysis by Royden is probably another one. So if you can get your hands on these books and just browse through them. And yeah, Rudin wrote another book. It's called Real and Complex Analysis. That's the big Rudin. That's the book that has a cult following. Some people hate it, absolutely hate it, and some people absolutely love it. It's the best book ever. So it's about real and complex analysis, as you might think, which is advanced calculus on steroids. Then Rudin wrote this book, and the thing about this book is it's so elegant. Elegant in the sense that it's super concise, like he does not waste a word. Like when he writes down a proof, he writes down the minimum number of things to prove it. So on one hand, oh yeah, it's nice, it's beautiful, but on the other hand, you're going to be reading from one sentence to another and not know what the hell happened between those 2 lines. Because he omits a lot of things that he says, this should be clear to you by now, come on. So some people really hate it because as a beginner, learning from this book from the first time is a nightmare. But once you actually get through it and look back at it, it's like, man, that was amazing. Right? This guy covers things in 10 pages that other textbook takes 70 pages to cover. Like literally, I've counted. I've looked at it because I use this in one of the classes that I was taking. And by page 30, he mentions this theorem and he proves it like that. I'm like, I don't know what the hell's going on. So I started looking at other sources and I'm like, they didn't prove this till like chapter 12, like 90 pages into the book. This guy gets to it at page 30, right? So some people love it, some people hate it. But yeah, this is by far the most common book for advanced calculus here. These are semi-common. Your professor might choose to use other books. So we're going to just look at some of the highlights of this. Basically, we're going to look at setting up the number system. We're going to look at what it means to be a natural number, what it means to be a rational number, what it means to be a real number, and the axioms that define these things. And we're going to analyze those. Some facts. This is really the guide that this chapter is going to tell you what the difference between a real number and a natural number really is. Yes, I know there are more real numbers than there are natural numbers, but what's the actual difference? Like mathematically speaking, algebraically speaking, what makes one special, right? Or what's the difference between the real numbers and the rational numbers? Because you might think the rational numbers should be good enough, but we're going to find out in a lot of ways they're not. So let's look at section 1. So this is chapter 1.1, section 1. This talks about the set of natural numbers. Okay. So we're going to look at the definition, what defines this set. And that's basically going to be the highlights. Because it also, after talking about the natural numbers, it then talks about induction. We've already covered induction. So the highlights here, things that you should know about are the piano axioms. Right? These are the very famous axioms. If you hear anyone referring to the piano axioms, they're talking about this one. It's just the set of axioms that define what it means to be a natural number. So it says axiom 1. Right, and remember, axioms are just statements that we take on faith, pretty much. We just believe them. There's no proof. So we can create a set n. It can get more general than this, but I'm going to write it down. We can create a set that we call n, such that 1 belongs to n. Axiom 2. If n belongs to n, so does n plus 1, which we call the successor of n. Axiom 3. So we know that the number 1 is in the set. For any number that's in the set, if I add 1 to it, that is also in the set. Axiom 3. 1 is not the successor of any guy in the set. Meaning 1 does not follow, it's going to be basically the first guy. Fourth axiom, any set any subset which contains 1 and contains n plus 1 whenever it contains n must be equal to n. And this is, did I write down? I should have written down 5 things. This should be the 5th one. Relate that. Or I can just call that 4. I'll mention the 5th one. Technically, your book calls this P5 because they like to end with a bang. This is the guy that makes induction work, right? This assumption here is what creates mathematical induction. The fact that when you if you contain the first guy and you contain the successor of everyone after that, you will literally contain all of n. So in other words, if you pin these numbers to a statement, if you can prove the first statement is true and prove that whenever one statement is true, the next statement is true, you'd approve the statement for all the numbers, right? It's kind of piggybacking on this. So they like to end with that one, but I guess I forgot to copy this one. If n and n have the same successor, then they must be the same number. Those axioms define the natural numbers. This is essentially what it means to be a natural number. So the point of axioms is that, one, they should seem obvious, so if it feels like I wrote down things that are obvious to you, that's good. It's a good set of axioms. which is one of the reasons why the axiom of choice was so controversial. It's not technically obvious how we'd always create that function. So it should be obvious, and it should be very minimalistic. It means you never assume too much. So you want to find out the minimum things that you can assume that are not very exciting, not obvious, that you can derive everything from. Right? So we don't want to assume too much, because then we run the risk of creating inconsistencies. So that was basically the highlight of this, talking about what the set N is. And it's just a set that obeys these rules. Right? So N is not terribly exciting, it's just how we count. So 2 goes to talking about the set of rational numbers. And I'll talk more about its properties soon, because the rational numbers are a field, and it therefore follows the field axioms, which I will actually mention, but they mention some other things first. So let's talk about that. Definition. So we also spoke about, and again, we also kind of spoke about Q is just a set of ratios of integers. The integers are the natural numbers with 0 and the negatives of the natural numbers. So if you take all of that set, the ratios where the denominator is on 0, you form Q. And then we can talk about some interesting things here. So a number is called algebraic if it solves a polynomial equation with integer coefficients. Technically, you could say rational coefficients, but because if you have rational coefficients, you can always just clear the denominator by multiplying by the LCD and create a polynomial with integer coefficients. i.e., x is algebraic if it is a solution to, these C's are A's. I think your book uses C's. C n x to the n plus C n minus 1 x to the n minus 1 plus C1x plus C0 equals 0, where the Ci are elements of Z. Or some places say are elements of Q. They're both countable sets, so there's not going to be much difference. And if your coefficients are in Q, you can multiply through by the LCD of all those coefficients, and you get coefficients in Z anyway. And n greater than 1. Here are some facts. All elements of Q are algebraic. Right? So if you have a rational number, there is some polynomial out there that it will solve. So I didn't write it, but say P over Q is in Q, then it solves a linear equation, right? It will solve that equation. If I plug in P over Q here, it solves this polynomial. This is a first 3 polynomial. This is an integer, that's an integer, so that's my C0 is P, and my C0 is minus P, my C1 is Q, and it will solve that. So all these guys are algebraic. We can always solve polynomials with them. Polynomials having integer coefficients. It turns out that some irrationals are algebraic. Not all of them. For example, radical 2 is algebraic. Right? Because radical 2 solves what? It is a solution to x squared minus 2 equals 0, which is a polynomial with integer coefficients. But not all of them are algebraic. If we extend to complex numbers, then I is algebraic. Right? I is a solution to what? X squared plus 1 equals 0. So guys that can solve polynomial equations, these are called algebraic numbers. They might look weird. Any number with rational exponents are algebraic. So any guy that looks like basically the square root of some number or the cube root of some number or any integer, right? Or any n to like p over q, right? They'll all solve some polynomial equation. So any number that's algebraic, if you raise it, any algebraic number, if you raise any of these algebraic numbers to rational powers, they remain algebraic. There's still a polynomial that they will solve. Things can be complicated, even something like take the number x equals the cube root of 3 plus radical 7 is algebraic. Now sometimes to show something's algebraic, you can just actually construct a polynomial from it. So what you can actually do, we can create a polynomial that this will be solved by this number. What I can do is I can cube both sides. Right? That will give me 3 plus, let's say radical 7, yes. 3 plus radical 7. And then I can move the 3 over, right? Because radical 7 is going to be a problem because it's not an integer coefficient. So I want to square both sides. So this would give me x to the 6 minus 6x cubed plus 9 equals 7. And so that would mean x to the 6 minus 6x cubed plus 2 equals 0. So this is actually the solution of a polynomial with integer coefficients, that polynomial in particular. And you might say, complicated things like that happen. You can do it with anything. So I'm sure you felt the tension building up in the air, leading to the fact that not all numbers are algebraic. There are non-algebraic ones. So don't think that it's a pointless definition. There are numbers that are not algebraic. Meaning you cannot come up with a polynomial that that will solve them. Such numbers are called, you know what we call numbers that are not algebraic? Transcendental. So back in calculus, when you had that textbook, early transcendentals was the subtitle of the calculus book. It was talking about numbers like these. Examples are ones you've heard about. Pi is transcendental, E is transcendental, right? Which calculus deals with, right? That's why they're called early transcendental. It's one of the few transcendental numbers that you encounter very early on in your mathematical career, because they tend to be very exotic numbers. So things like ln of 2 is transcendental. 2 to the radical 2 is transcendental. E to the pi to the e is transcendental. I is transcendental, but I raised to the ith power is transcendental. So there are a lot of transcendentals. How many? The set of algebraic numbers is countable. Which means the set of transcendental I feel like I'm spelling that wrong. Numbers is uncountable. So it turns out that most numbers on the real line are actually not solutions to polynomials of this form. Most numbers are transcendental. So a lot of the numbers are transcendental. You can take all the real numbers, throw away all the guys that can solve polynomials with rational coefficients, and it would not make a difference to the size of the set. So those are some things that just introduced. I don't remember if your book introduced this, but Louisville's constant, did it talk about that? Anyone who was reading it? It's another famous number. It's this guy. 10 to the minus k factorial. So this is going to be 0, 1, 1, 1, 1, 2, 3, 1, 1, 2. Basically, the idea, it has a 1 in all factorial positions, zeros otherwise. It is transcendental. So look at the 1 factorial, the 2 factorial, the 3 factorial, the 4 factorial, the 5 factorial. Look at those positions and put a 1 in those positions. If you, and in all other positions fill it with 0, you would create an infinitely long decimal expansion, and it turns out that it is transcendental, which means it's not a rational number. Because all rational numbers are transcendental. So there are weird animals like that. I think we only have time to state this, so I'll state it. So a very important, probably the biggest deal here, which is what you need this to answer, is the main theorem in section 2 is the rational roots theorem. Which some of you would have heard about since way back in pre-calc. At least your teacher would have told you, oh, we can do this thing. The reason why you can do that thing is because of the rational roots theorem. You've never seen it. It's a breakdown in the big education system, and I apologize. But it's a very important theorem. It says, suppose R is rational, is a solution to this polynomial Cn x to the n plus Cn minus 1 x to the n minus 1. Da, da, da. Suppose you have a rational solution to some polynomial equation where Ci is in Z and n is greater than or equal to 1. Cn not equals 0. So the n degree polynomials and C0 not equals 0. Okay, so suppose you have the rational roots there. Then R is of the form R will be of that form. It will be plus or minus this ratio. More specifically. If we let R equal C over D, D not equals 0, and CD have, it's in fully reduced form, no common factors. Then it must be the case that the C will divide C naught and the D will divide Cn. It's important that you realize that this theorem doesn't tell you that there will always be a rational root, because that's not true. But if one exists, then it must have this form. I.e., if, and that's a big if because it might not be the case. If a rational root exists, it must have the above form. We'll finish talking about that tomorrow, but we'll stop there for now. We finished chapter 10. We'll look at this theorem. We'll also look at the field axioms tomorrow, and as well as the completeness axiom, which is what separates the real numbers from the rational numbers. So, yeah, homework for chapter 10 due tomorrow. You can start downloading this book and start reading through it. Because I want you to work on the homework, I'm not going to give you the take-home today, so the take-home I will post over the weekend. Sunday the latest, I'll give you. I think 1 day is enough, but I'll give you 2 days, maybe. So you bring it to class on Tuesday, you just print it out and fill in the space. So it'll look like just like a regular test where you'll do the problems. So yeah, if I'm around Tuesday because I'm giving the final in my other class. But if you don't see me, you can just go to the math department and drop it off there by the end of the day, and I'll pick them up when I leave. So we'll stop there. I'll see you guys tomorrow, or we'll wrap up.